Okay. So let me begin by thanking the organizers for giving me a chance not only to talk to the technical people but also to the public of Groningen, the city. Though I can't see you, I'm sure you are all there and won't walk out halfway through the lecture. Now, the topic addresses some of the cosmic questions which virtually everyone has wondered about. What is the cosmos made of? How does the universe evolve? And people have heard about things like Big Bang and expanding universe and things like that. How does it do? And finally, the most important question, where did it all come from? Why is there something rather than nothing? These are the questions which people have been wondering from the days of pyramids. When you are lying in desert and watching the skies, these are probably the first questions which comes to your mind. So one might think that cosmology is a very old science, but that is not true. In fact, cosmology is probably the youngest of all sciences, and my personal favorite for its date of birth is somewhere around 1990. So it's probably about 25 years old. This is because in order to qualify something as science, it is not enough that you have beautiful ideas and wonderful speculations and philosophical insights. You need data, you need observation, you need numbers, and that is what characterizes science, away from idle speculation. And that happened in cosmology pretty recently. From 1990 onwards, thanks to the superb improvements in technology, we have come to understand a lot more about the universe. So I would put the date of birth of the universe around 1990. Now the cosmology today is a completely observational science, like solid state physics or nuclear physics or things like that, except it's slightly more benign science than some other sciences. But it is not led by theoretical speculations, and that is what one message you should take home with. The reason it works is because cosmologists are a privileged lot. They can actually see the past. They can literally see the past. That is because when I am looking at any one of you, I don't see you as you are right now. Light takes certain amount of time to come from you to me, which means I am going to see you as you were a fraction of a second earlier. So if I look at objects which are farther and farther away, I am looking at them when they were at earlier and earlier periods. So by just having a way of looking at with any kind of telescopic structures further and further away into the universe, I am seeing the universe as it was billions and billions of years ago. I can actually see the universe how it was in the past, and that is only possible in cosmology. So clearly, if you want to see further and further away, you need more and more powerful instrument. That is where technology comes in. The developments in technology now allows us to see the universe very far away, as a result of which we can actually ask the universe, hey, how were you 30 billion years ago, or 15 billion years ago, or 10 billion years ago, etc. And then get the answers from it. You don't have to speculate. You can actually see it. So this is just a host of observational devices which an astronomer uses. And coming from India, I have put in two major instrumentations which we have in India. This is a satellite devoted to astronomy called AstroSat, and this is the largest radio telescope operating in these wave bands, which is located near my where I work in Pune. It's called GMRT, Giant Meter Radio Telescope. So once you have all these data, cosmologist's task is very simple. He does something like this. Okay. So what exactly is all this? It's pretty simple. What it does is one of the two things. At the top of this slide, I have the structure of physical laws, what the physical laws about the universe or what we understand in the laboratory, etc. tells us. And then there is the structure of the universe. Most of the time, cosmologist is doing one of the two. He will either use the structure of physical laws, what we know about the physical laws, to explain the structure of the universe. This has been an extraordinarily successful enterprise. We do understand now today with very high level of confidence what the universe did from a fraction of a second after the Big Bang to about 14 billion years. By any standards of science, this much of spread over time where we understand a system is remarkable, and that is what cosmology has achieved today. This is great, and I will allude to a few of these things as we go along. But what is really exciting is what happened before this 1 billionth of a second, or what is going to happen in the future. Because we would always like to push the boundaries of our knowledge and go into the unknown. So for that, what we need to do is to understand what happened before this, and we want to test the physical theories, not use known physical theories to explain the universe, but test the physical theories using the structure of the universe. So that goes from the structure of the universe to the physical law rather than the other way around. So I want to talk to you about both these approaches. So I want to begin by telling you what the structure of physical laws is, and then I will explain a little bit about the structure of the universe, and then we will see how the interplay works back and forth. So let us start with the structure of physical laws as we know today. The physical laws today can stand on three pillars which are given there. One is Newtonian gravity. This is the gravitational interaction described by Newton. The other is special theory of relativity, and the third is what is called the quantum theory. So let me just take you through each one of them. Newtonian gravity just tells you how the gravitational force acts on the universe. And this governs the entire physics of the macro world. Everything from solar system, planets going around the sun, the dynamics of galaxies, dynamics of clusters, most of the macro world phenomena is completely described by the Newtonian gravity to a great extent. Then comes special theory of relativity. Everybody knows that. Everybody knows E equals mc square. Many t-shirts have it. Okay? So I don't have to even explain it to you. What Einstein did in special theory of relativity is essentially to say that space and time should be combined into a structure called space-time. So you no longer think of space as some absolute thing and time as some another absolute thing, and then you think of them as two different things, but it is merged into a single continuum called space-time continuum. This is special theory of relativity, and one of the offshoots of that is E equals mc square, which we have in our t-shirts. The third is the quantum theory. Just as Newtonian gravity governs the physics of the very large scales, quantum theory governs the physics of very small scales. There, the most important principle is something known as Heisenberg's uncertainty principle. What it tells you is that if I have an object, if I have a football, this is the football season, and I kick it, most of the time it will go where I intended it to go. So at any given time, I know where it is and in which direction it is moving. But if you kick an electron rather than a football, you will not know which path it will take. You will not know at the same time which is the position and which is the velocity or the direction in which it is moving and with what speed it is going. It is like a bad footballer kicking a football. So the electrons or most of the atomic particles, like the molecules and many of the microworld particles, behave obeying this uncertainty principle. This also means that there are some intrinsic fluctuations in the quantum world, and this is what quantum theory tells you. Now we can combine these pairwise. You take Newtonian gravity and special relativity and combine together, then you get something known as general theory of relativity. This was probably the most beautiful of all physical theories which we have. What it tells you is that gravity is not a force at all. Gravity is essentially due to curvature of the space-time. What does that mean? Imagine something like this. Think of this as some kind of a mattress, and I have put a heavy ball here which is sort of curving the mattress. Now if I put a light ball here, that ball will roll down. Now if you didn't know there is a mattress, you will think that this ball is attracting that ball. So there is a force of attraction between two of them. What is actually happening is that one object is curving the space-time and the other object is just moving along straight lines in that curved space-time, and that appears to you as though there is a force of attraction between these two. So what is essentially known is how much does it curve. So suppose I take an object and I bend it. I take a metallic rod and bend it. If I bend it quite a bit, then I can draw a small circle here. So the radius of that circle is small, means I have bent it quite a lot. Large curvature means small radius of circle, and vice versa. What this equation tells you, incidentally, showing equations in a public lecture is considered to be a criminal offense in several countries. I hope this is not one of those countries. And insulting the intelligence of the audience is also considered a worse criminal offense in many countries. So I don't want to do the second crime, and I would stick with the first one. So those of you who don't like equation can just ignore it. I will be explaining it in English. So what it tells you is that there is some amount of energy which is present here, because mass and energy are the same. Remember the t-shirt, E equals mc square. So energy and mass are the same, and that energy which is present in some region is going to curve it, and that curvature will be very small if this energy is large, and vice versa. So a lot of energy, strong curvature, and vice versa. This is what Einstein said. So we combine these two, and now let us go and combine these two, special relativity and quantum theory. That leads to a branch of science called quantum field theory. The most important thing about quantum field theory is that what you thought was empty space is filled with fluctuation. So this is an artist's picture of the fluctuation. This constantly, there is energy which is being created and destroyed, and there are virtual particles mingling around. And to every particle, there is an antiparticle. You must have heard of proton, neutron, and electron, which are there in an atom. To an electron, there is an antiparticle called positron, which is, for all practical purposes, is like electron, but it has a positive charge rather than the negative charge of the electron, negative electric charge of the electron. So again, this looks like science fiction, but if you are unfortunate enough to go to a specialist hospital, they might do what is known as a positron emission tomography, PET scan. The PET scan is something which you might have heard of, and medical students will definitely know. The P in that PET stands for positron. So it is not an esoteric object at all. Every specialist hospital has it now. You can create positrons and electrons in the laboratory, and these positrons are even useful for you. So to every particle there are these antiparticles, and our standard model of particle physics people have built up entirely depends on this quantum field theory. So we have come up to this, and finally I want to combine this general relativity and quantum field theory and get to what is known as quantum gravity. Unfortunately, I don't yet have a picture to put there. The stamp has not yet been issued, so I'm leaving it blank for the moment. This is the unknown final frontier of physics, which many of us are working on. This is needed in cosmology. When you go to the earlier and earlier epochs of cosmology, you need to know what the quantum mechanical laws of gravity are, and we will come back to it in the end of the talk. And it can be tested by cosmology. Remember, I told you that it is all fine to say that from a billionth of a second to a very large 14 billion years we understand the universe. But what is more important is what happened before the billionth of the second. If you want to do that, you need these quantum laws of gravity, which we don't have, but we hope to get one of these days. That is a rapid introduction to the structure of physical laws which we will be using. Now let me come back to the structure of the universe, which is relatively simpler. So here is a picture of what you will be able to see around the sun. This is sun, and this is Alpha and Proxima Centauri, and many of you who are stargazers will recognize many of this. This is Sirius, which is the brightest star in the heavens, and this is the way things are distributed around sun. Go a little further, you will find something like this. You again have sun here. This is Rigel, this is Betelgeuse in Orion, this is the Orion's belt, and then you see these bands. You find that the stars are organized in some kind of a band structure. So we have just zoomed out. This distance is like 1,000 light years. What are these bands due to? These bands are due to the fact that we are living in a galaxy which has these spiral arms. Okay, these arms are named after the prominent constellations in the direction of that. Now we are at 10,000 light years away, and this is a galaxy. This is our Milky Way galaxy, and we were somewhere over here, orbiting in that galaxy. If you go still further, so far in this, every dot, so to speak, is a star. Now we are too far away, and so every dot here is a galaxy. This is a Milky Way galaxy. The nearest large galaxy to us is Andromeda galaxy, which is falling towards us. And there are all these tiny, tiny dots, which are all galaxies, which are gravitationally bound together. This whole region forms a part of what is known as a local group of galaxies. So they are all a gravitationally bound system, like planets are a bound system to the sun. So far this was artist's concept based on data. This is a real photograph of the Andromeda galaxy. This is the kind of galaxies which you see in the sky. And they come in a wide variety of sizes, shapes and patterns. So we have a veritable zoo of galaxies, and these are all now accessible to our telescopes. If you take still larger view of the sky, this is what you will find. The groups of galaxies, like the local group I told you, form together clusters, and these are some very large clusters of galaxies. The Coma supercluster, for example, has nearly thousands of galaxies in this. And you see that the galaxies are distributed in some kind of a filamentary shape, and there are also large voids in between. So the galaxies are not distributed like a nice cubic array of atoms. It is also not distributed completely randomly. And understanding how they are distributed is one of the major issues in cosmology. When you read poetry, certainly in English poetry, poets are very fond of talking about star-studded heavens. That is because poets can only see stars. If only you have eyes to see galaxies, night sky when you go out will look like this. Each dot in this is an actual galaxy. This is put together by very careful observations of what is known as automated plate measurement, APM survey. So every one of them is a galaxy, and you can see these sort of filamentary structures which is over there. It would have been beautiful if only we can see every galaxy in the sky. There are nearly over 1 million galaxies in this region, which I am showing you. And the same thing happens even when you look at the galaxies from one point. Here you are sitting here, and this is the direction. This is like a pizza slice. You are going in one direction, and this is the angular direction. And you find there are large concentration of galaxies here, and there are also void-like regions here. So this is the picture which we have, and now I want to get to the dynamics of this structure. So are these galaxies just staying there, staying put there? No. Nothing in the universe is static, and the entire universe itself is expanding. It is expanding in the sense that if you take any two galaxies today and you come back and measure the distance between them tomorrow, it would have increased a little bit. So the universe is not an abstract entity. Universe is just a collection of galaxies. So when people say universe is expanding, it is not like a balloon expanding into the outside. There is nothing outside the universe. So universe cannot expand into something. What we mean is that the universe is just a collection of galaxies. The distances between any two galaxies which are sufficiently well separated is increasing with time. That is what we people say when you sort of talk somewhat loosely that the universe is expanding. This is what is meant. Now I want to give you a simple argument by which you could have figured out that something like expansion of the universe should take place, which you can do by going out tonight. And in this season, in this country, you had to go out at probably 12 o'clock. And if you go out and you do see the sky, you can ask yourself, why is night sky dark? You might think that is a silly question. It is not a silly question at all. The point is that let us assume the universe is infinite in all directions, and let us assume universe is made of stars. The same argument works with galaxies, but let us assume it is made of stars. It is static, it is not expanding, and there are all these stars all over the place. Now you take from Earth any direction. If there are infinite number of stars, then you can convince yourself that any direction will hit the surface of a star sooner or later. Sometimes it will hit very soon, sometimes a little later, sometimes you may have to go a long distance before you hit. But it will always end at a star because there are infinite number of stars all around you, uniformly distributed. Now, the interesting thing is that when the star is moved further and further away, the size it shows for you is like a mountain very far away, it subtends a small angle to you, and if mountain nearby will subtend a large angle to you. Thus, the surface of the star, the size which you perceive, falls as the square of the distance. If you go twice the distance, it will fall down by a factor 4. So that is what it says. But at the same time, the light from the star to you also falls down by the same factor. If you move a bulb twice as far away from you, the intensity of light which you are going to receive is going to be 4 times smaller. This means that the amount of starlight per unit area on the surface is not changing. The area is coming down, the amount of light coming from it is also falling. They are falling by the same amount, so the amount of light from unit surface area, 1 square centimeter of the surface area, is not going to change. That means that the night sky, since it is always going to hit a surface of a star, should be as bright as the surface of the sun. What is happening? But then why is night sky dark? One of these 3 assumptions here must be wrong. We know today that the universe is not static. This argument does not hold in an expanding universe. So this is known as Olbers Paradox, which has been resolved with the expansion of the universe. So the expansion of the universe is not an esoteric concept. If the night sky is dark, universe must be expanding. So this is what I said about the infinite expanding universe. Think of this grid extended in all directions infinitely. Then what is happening is that these dots are just moving apart. So just by looking at these dots without worrying about where the rest of the universe is, you can figure out that it is expanding. So you only need this much to know that the universe is expanding. You don't have to ask what is happening at the edges. So what is driving the expansion? The engine which is driving the expansion of the universe is an equation given by Albert Einstein. It is written in tensorial notation like this. You don't need to know what it is, but it is from Albert Einstein, therefore it must be right. And this is a basic equation in general theory of relativity, which tells you how fast the universe is expanding. So I told you that in Einstein's theory, the curvature is decided by the amount of energy density. And this idea, if you talk in terms of expanding universe, what it tells you is that given the amount of energy density, you know what is the curvature. And once you know the curvature, you can ask how long will it take for the universe to double its size. It is just the radius of curvature divided by speed of light. So today the universe is doubling its size once in every 14 billion years. When the universe was very small and very compact, it was doubling its size once in every second. So this is something like the government bonds. These things double at every, say, 6 years, 5 years, 7 years. So the size of the universe is doubling at a particular rate. In particular, if this radius of curvature was constant, it will keep doubling at that rate. And most of the time, as it doubles, the radius of curvature will change. As a result, you have to do this. How do we know all this? I told you right at the beginning that cosmology is no longer about idle speculation or philosophy, and I have given you a story so far. But this story is put together with a huge amount of observations, and one of the key observations is that if the universe is expanding, in the past it would have been hotter, and we should be able to see the radiation from that hot phase. And that is called the cosmic microwave background radiation. It is as though we are sitting inside a microwave oven, a huge microwave oven, and the oven's temperature is set to 2.73 Kelvin, which is like minus 270 centigrade. So this is the temperature of the universe today, and it has been very high in the past and it has been cooling down. And this is what is known as the smoking gun of the Big Bang. So I have told you about the structure of physical laws, structure of the universe, and how we know that the universe is expanding, roughly speaking. So next comes the most important question. What is the universe made of? So this, most of the time, observers like to talk in terms of a parameter, which is denoted by the symbol omega, which is the last letter of Greek alphabet. It essentially measures the relative strength of the expansion compared to gravity. Think of it like a stone which has been thrown upwards. If you throw a stone upwards, it will go up to a maximum radius and come back. Why does it do that? Because it has an expansion speed and there is a gravity which is pulling it down. If the gravity wins over the expansion speed, it will go up to a maximum size and come back. On the other hand, if you want to send a satellite to Jupiter, you want to escape from Earth's gravity, so you shoot it up with larger speed than the gravity can overcome. So there is an escape speed. So this is essentially the ratio between these two, the speed at which the universe is expanding and the amount of gravity which is present in the universe. If this omega was strictly equal to 1, it is like a stone which is thrown upwards exactly at the escape velocity. If omega is greater than 1, then the gravity wins over the expansion. The universe will expand up to a maximum size and will then contract back. If omega is less than 1, then the universe will expand forever. So what we want to know is how much is this omega of the universe. Now the first thing you do is to go and measure all the galaxies which are there in the sky, and you can compute all their masses and you know the expansion speed from observation, and you can put them all together. Then you find that the omega is about 0.05. So which is like, if you think of omega equals 1 like 100%, about 5% of what you need in order for the universe to reach a maximum size and then contract back is all that you have in all the galaxies which are there. But then you can ask the question, is that all? In the sense that, is there anything in the universe more than what meets the eye, what is emitted by the light? Now it turns out there is a lot more. So this goes under the name dark matter. So I want to just give you a description of that. Here is a galaxy, and in that galaxy there are tiny gas clouds which are going around the galaxy. These are hydrogen gas clouds, and they emit radiation, and you can detect that radiation on Earth, and from that we can figure out with what speed it is going around. That speed you can relate to the amount of matter which is inside. So you know, if there is this luminous matter is all there is to it, the rotational speed of these objects at various distances, this radius is the distance from the center and this is the speed which it is rotating, you expect it to go like this. What you find, this is just a typical figure, there are hundreds of galaxies for which it has been done. What is found is that observationally this is how it goes. This is because there is a lot more matter which fills this gap in between, which is surrounding this. So the galaxies are sitting in very large halos of dark matter, and this dark matter doesn't emit light, but it does influence things gravitationally. Here is another example. If you look at it, you see these slender objects like this, and you can even see, sort of imagine that there's some kind of a circular arc here, there are all these distorted things. What is going on here? What is going on here is that these distorted objects are very distant galaxies, and the light from those galaxies are coming through a cluster of galaxies nearby. So there is a light from a distant galaxy which is coming through this cluster of galaxies, and the light bends because of the gravitational field of this nearby cluster, and it also gets distorted, so the shapes change. So by looking at the change in these shapes, you can measure how much matter is out there. That counts all the matter which is there, not just the matter which is emitting light. So as a result of which, people can actually find out how much matter is there, even though it is dark and it is not emitting light. When you do all that, you get a number which is another 26%. So what you have got so far is that you have normal matter whose density will keep decreasing. The density of matter in the universe will keep decreasing when the universe is expanding. Okay? Don't worry about the actual nature of the curve. This is just to show you that it keeps decreasing. Then there is dark matter in the universe. It has to be dark. It is drawn in black line. So the dark matter in the universe at any given time is about 8 to 10 times more than the normal matter, and that is also decreasing as the universe is expanding. But I also told you that from the primordial universe we are getting radiation. And it is like we are inside a microwave cavity with some temperature, and there is a lot of radiation, radiant light in the universe. And the radiation falls faster than this. It again falls, but it falls steeper. So the total cosmic energy density, the radiation has energy and matter, E equals mc square, has energy. So if you take the total energy that follows this red curve, this is the total amount of energy. And there is one point at which the amount of radiant energy and the amount of energy in normal matter or dark matter is equal. And this is called an epoch of matter radiation equality. This happened when the universe was typically 10,000 times smaller. Take the present size of the universe, go backwards, it was smaller and smaller. When it was 10,000 times smaller, this happened. And we know what was the density of the universe at that time. Just remember that this is a number which characterizes the universe, which is measurable. We know what its value is. Let us go further. The next thing which we want to do is that all these galaxies and clusters of galaxies and all these must have formed by some process. Do we know how it got formed? Can we figure that out? So the easiest way to do this is to make a universe. And I will show you how to make a universe. So here is a picture. So you start with a universe which has very small fluctuations in the energy density and run it in a computer. And this is what happens. As time goes on, you will find that rich get richer and poor get poorer. And the places which has more density acquires more mass, and places which has less density will lose out on that mass. As a result of which, let me run it once again. As a result of which, starting with tiny density contrast at various places, you are going to get structures, these kind of filaments and these kinds of voids which I talked about. The kind of universe which you see today can emerge out of this. So we do understand that in gravity, if you start with some tiny fluctuations in the beginning and you let gravity take its course, you do get this picture. But where did you get this tiny fluctuation? I told you long back. I told you that quantum field theory tells you that empty space is not empty space. There are vacuum fluctuations in the energy. So it is these microscopic vacuum fluctuations in the very early universe which has led to very large cosmic structures which we see today. This is a remarkable synthesis which has come up in the last 2 or 3 decades, and we think that this is how these structures have got formed. That is good, but let us not speculate. How do we test this idea observationally? How do we know this idea is correct? How do we know this is how the structures got formed? If this is correct, then I told you that this cosmic microwave background radiation has this temperature. Well, I wasn't being very accurate. If there were tiny perturbations in the universe, those perturbations will reflect on this cosmic microwave radiation. So if you look at the temperature in one direction and temperature in another direction, they won't be exactly the same. There will be tiny wiggles in this temperature. So there are hot regions and cold regions in the sky. This is what is called the microwave sky. This is just the surface from which this radiation is coming, and this is coming from a time when the universe was about 1,000 times smaller. We have a freeze frame picture of the universe when it was 1,000 times smaller. There were no galaxies, there were no stars, it is just this light. And this light had these tiny wiggles. How tiny? About few parts in a million. Or let us say 1 in 10,000. That is the kind of fractional temperature difference. So with the technology which we have, we can measure them. And these tiny wiggles contain a goldmine of information. And in fact, this is where my date of birth was quoted for the universe came from. 3 satellites, COBE, WMAP and Planck, roughly 10 years apart, has got the picture which is this different. The first one was very coarse grained. This is high resolution. This is like high density TV which you are watching. So just technology improvement has allowed us to probe the universe with this level of details. And we actually know how these structures are behaving. So you have these fluctuations imprinted when the universe was 1,000 times smaller. And this has come from the vacuum fluctuations very early in the universe. and this has led to the cosmic structures which we see today. This is the in-between anchor. Interestingly, if you look at this second part first, how this could have evolved into this, which is essentially because of gravity, rich getting richer and poor getting poorer. This depends on the nature and the amount of matter which is present in the universe. If you change the contents of the universe, if you tinker with it, you will start from this, because this is observation, and you won't end up getting this. You will get something else. So in order to go from here to here, both which are anchored by direct observation, you need precisely some kind of amount and nature of the matter in the universe. And when we did that, it turns out that it has a very weird composition. The universe has a very weird composition. It has about 5% of normal atoms of which you and I are made of. There is about 26% of what I have said is dark matter. But the remaining percent, it actually adds up to 1, but the remaining percent is not matter at all. It is contributed by a term in Einstein's equation, in Einstein's theory, which goes under the name cosmological constant. This is what sometimes in popular literature you will hear as being mentioned as dark energy. The moment I say dark energy, it is Star Wars, Dark Vader, all kinds of ideas will come in, so I don't want to use that. And all observations are consistent with it being just a term in Einstein's theory. And if you have this kind of a combination, then this structure implies that this is the composition of the universe. Nobody wanted the universe to be made like this, but that is what observations tell us. So this cosmological constant was something which Einstein originally suggested for a completely different purpose. As I said, it is just a term in Einstein's equation which behaves like matter with negative pressure, but it is not matter at all. So you don't have to worry about it. It is just a mathematical idea. It is a fundamental constant of nature. And it has a very peculiar property. It drives an accelerated expansion of the universe at the present epoch. What do I mean by that? Think of the expanding universe like a car which is going in one direction. It can go with a uniform speed, or it can go with an acceleration with the speed increasing, or it can decelerate and slowly coming to a halt. People believe that the universe must be slowing down and it must be decelerating, but observation suggests that it is actually accelerating, and this cosmological constant can drive this accelerated expansion. And in fact, most theoretical physicists consider this to be the deepest riddle in theoretical physics today. We don't understand what the cosmological constant is, and it's a very deep mystery about the universe. So I said that if there is a cosmological constant, it will accelerate the expansion of the universe. Again, cosmology is not speculation, cosmology is not philosophy. It is direct, hard facts based on observation. So we want to go back and ask whether there is an observational signature for it. Indeed, there is. If you want to know how the universe is, whether the universe is accelerating or decelerating, you need to compare the speed with which it is expanding today with the speed with which it was expanding, let us say, when it was 1/3 the present size. So you need to know with what speed the universe was expanding when it was 1/3 the present size. So you need to know the freeze frame picture of the universe in the sky available to you at that time. The only thing is that if you want to look at things which are earlier and earlier in the universe, you have to look at objects farther and farther. There is a small problem that farther and farther objects will look dimmer and dimmer. So with a given technology, you can only go this far and no further. Fortunately, there are objects called supernovae, which are very mighty stellar explosions in which some of the stars end their life. And these are beacons of light which are visible for a very large distance. So in fact, this is really an interesting thing. Since this is a public lecture, let me mention this. All the material which we see, all kinds of elements in the periodic table, only 2 of them, hydrogen and helium, were synthesized very early in the universe. Rest of it was all synthesized inside the stars, and thanks to the supernova explosion, they were spewed out into the interstellar medium, and planets like Earth formed out of this. So we are all star children, and that is how we have this elemental abundance which is there in Earth. So supernova is a very important concept for that. So this is one of the supernovas which went off in 1054 AD, and this is the relic of that supernova called the Crab Nebula. I am absolutely certain all of you can read Chinese. This is the Chinese description, Chinese astronomers' description of this supernova, which was a very bright event. It actually went off on 4th of July according to some of the estimates. There could be some uncertainty about it, so we are pretty close to that. And this particular supernova was visible during daytime, and it was visible for nearly 20 days during the daytime, and it was recorded by early civilizations in many parts in the world. So now, of course, with technology we have large number of such supernova, and using this supernova we can actually measure what is the speed of expansion of the universe as a function of the size of the universe. Let us assume the size of the universe was this size. When it was 90% the size, 80% the size, 70%, 60%, 50% of the size, we can measure with what speed the universe was expanding. Now, you don't have to be an astronomer, or you don't even have to be a mathematician to look at this picture and say that the speed was decreasing, so the universe was decelerating, and then the speed is increasing, which means the universe is accelerating. So this is the evidence for the cosmological constant. The cosmological constant allows you to get this accelerating phase of the universe, and from that you can draw an important conclusion that if you look at the density of the universe, it doesn't keep falling to zero, it sort of reaches a plateau. There is a lowest energy density in the universe which is related to this cosmological constant, that is denoted by this Greek letter lambda. So the total cosmic density, which I told you originally had this kind of a picture, and I told you that there is one number here. Now if there is a cosmological constant, which we now know it is, it sort of plateaus out, so there is a second number for the universe. So there are two numbers which describes our universe, this one and this one. Now I said some time back that the existence of this fundamental constant called the cosmological constant is a major mystery. Now what is so mysterious about it? So let me try to describe this to you. This is the cosmological constant, and it has the dimension of 1 by square of the length. So it can be measured in 1 by centimeter square. There are a few other constants, 3 other fundamental constants which we know of relevant to cosmology. One is G, which comes from gravity, it is the Newton's constant. The other is H, which comes from quantum theory, uncertainty principle, etc. And the third is the speed of light, which comes from relativity. So you take this lambda, multiply by G, multiply by H, and then you divide by C cubed, which is C into C into C. Then you get a pure number. And this is one of the tiniest numbers known in cosmology. Now for those of you who are not mathematicians, let me explain what this symbol means. It means you take 1 and put 123 zeros after that, and then you take one part out of it. Like if you put 3 zeros after 1, you have 1000, and 1000 is a small number. If you put 10 zeros and you take 1 by 1 followed by 10 zeros, you get a still tinier number. So this number is obtained by taking 1 and you put 123 zeros after that. It will go all the way around this dome, and then you take one part out of it. It is such a tiny fraction is what this number is. So we do know from observation such a tiny number exists. Of course we don't directly measure this, we measure other things from which we get that. Theoretically we don't know what that number should be, and this number is again a signature of the universe. It doesn't depend on what units you are going to use. Like if I'm going to say what is the speed of the car, I can say it is 80 kilometers per hour, or I can say 50 miles per hour. So it becomes 80 in one unit but 50 in another, so that number doesn't have any deep significance. But this number doesn't change, it doesn't change depending on your units, so as a result of which we need to understand what it is. This is also closely related to the question as to how did all this begin, because this cosmological constant is a fundamental constant related to the universe, which means we need to know where it came in and how did the universe came into the being. This is, of course, fairly technical, but let me try to give you an idea, because people often wonder that can cosmologists ever explain the origin of the universe? What is cosmogenesis? Where did the universe come from? Now, it turns out that the universe is actually indistinguishable from empty space. That sounds very funny, because there is all this matter out there and empty space is empty space. No, it is not, because all this matter in E equals mc square is just energy. So there is so much of energy in the universe, and we want to know where the energy came from. Energy is supposed to be conserved in physics. So if there was zero energy, it will remain zero energy. Now you can actually measure what is the total energy in the universe. There is energy in the form of all the galaxies and dark matter and all that sort of a thing, and you can count how much of energy is there. But there is also energy locked up in the gravitational field. It turns out that the energy locked up in the gravitational field is actually negative. And if you calculate the total amount of energy, adding the positive energy of the matter with negative energy of the gravitational field, you end up getting zero energy for the universe. So the universe actually has zero energy, just like empty space. Let me give you just one more idea which will anchor this point. I said the universe is expanding, so the universe is going out radially like this. Why can't the universe rotate? Why can't the universe move like this? Why can't galaxies out there go like this and galaxies out here go like this? Why can't there be a systematic rotation of the universe? You cannot, because the rotation in physics is related to something called angular momentum. That is a conserved quantity. If originally you had zero angular momentum, then you will end up having zero angular momentum. You can't generate spin if originally there was no spin. So all the tiny structures like planetary systems, galaxies, etc. rotate. They have angular momentum, but the total angular momentum of the universe is strictly zero, and so is the vacuum. So we believe that the universe is just a result of this kind of a vacuum fluctuation, and there is already one density which came here, one number. There is another number which is related to this, which is the density contained in this cosmological constant, and then this contains some amount of energy, and that is the third number. These three numbers characterize our universe, and it is convenient not to work with this number, but to work with what is the sort of amplitude of this fluctuation, how big are these fluctuations. That turns out to be about 1 part in 10 to the 5. Again the same notation. You put 1, then you put 5 zeros after that, and then take 1 by that. So 1 by 10,000. So this is also measured, and we have these fluctuations, we know these numbers, and you want to understand them all. So mathematically, I have already told you that there is this number which is like 10 to the minus 123, and this is another number which comes from the fluctuations in the universe. Now it turns out that in the conventional approach to gravity, which I have been talking about all these times, about Einstein's theory and things like that, and with classical physics, there is no way of understanding this. It turns out that you need a completely new perspective to understand these concepts, and there is a very different paradigm which you need. And some of us have been working on this, and this is a frontline research, and many of the sessions today in the conference which we are all participating was devoted to this new paradigm. The new paradigm says that we still need to think about gravity in yet another different way. So we had already thought that gravity is no longer just a force, but it is a curvature of space-time. It could actually be what is technically called an emergent phenomena. What do I mean by that? Well, think of elasticity. Suppose I have a rod and I bend it. It will come back. It will vibrate. Think of gas dynamics. If you have a volume filled with gas, then you move a piston, the volumes of the gas will change, its pressure will change. When you pump air into a cycle tube or the cycle wheel, its properties change. These kinds of dynamics can all be described in terms of some macroscopic variables. But we do know that gases are made out of atoms and molecules and all these tiny structures. But you don't need to know what they are in order to explain how a engine works or a steam engine works, or how the pressure in a cycle tire is going to behave. So these are called the emergent dynamics. The emergent dynamics is like the outer layer of this physics. So it is like the fluid dynamics. So the gravity is just the fluid mechanics of some substructure, which I call, for the lack of better word, as atoms of space-time. Just as when you talk about the flow of water, water is made of huge number of water molecules. They are all flowing. But when you are studying the flow of water, you don't need to know what these are made of. So you can do that. And this was deep insight from an Austrian physicist, Boltzmann, long back, when you are studying normal matter. He said that the normal matter could be heated and cooled. Hot water and cold water both contain the same amount of molecules, both seems to be in the same state, but if you dip your finger into hot water, the consequences are different from dipping it into a cold water. That is because there are microscopic degrees of freedom in this water, and these molecules are moving with different speed. So if you can heat it, it must have some microstructure, and these microscopic degrees of freedom are needed. So we need to study gravity exactly the way people studied gas dynamics before the advent of atomic theory of matter. There is just one problem. The problem is that for normal matter, the atomic structure is something which we have tested in the laboratory, but the corresponding number here, this is 1 divided by 1 followed by 7 zeros. Here you have to put 33 zeros. It is an extraordinarily tiny length scale in which the atoms of space-time, that is atoms of space-time, is much, much smaller than the normal atoms which we see. People usually don't have a good feel for very large numbers and very small numbers, so I have drawn that picture here. So this is the outer universe. Here is the sun, here is the solar system, this is our galaxy, this is a cluster of galaxy, this is the cosmic microwave background radiation which we have been talking about. So that goes by factors of 10, 100, 1000, this is 10 multiplied 10 times, 10 multiplied 20 times, 10 multiplied 30 times. But you can also do it in reverse. This is 1 divided by 10 multiplied 10 times, this is 1 divided by 10 multiplied 20 times, etc. You can go in the microscopic scale. Then you have atomic systems, this is the nucleus. This is the scale at which, this large hadron scalar in CERN is operating, and this is the scale up to which we have direct experimental evidence. There is some kind of a theoretical ideas which goes all the way up to this. So if you go all the way from here to eternity in cosmic side, and you come back here, you reach somewhere here. But the systems I am talking about, called the Planck length, is still further removed. And here is where the principles of quantum theory and gravity has to be put together. And since we don't have a good theory for that, it is not directly accessible to test. So this is the situation which we are today. And in the last slide, I want to show you a formula, which of course none of you will understand, but that is not the idea. The idea is that this theory allows you to write down equations like this. Don't worry what that equation is. And you can verify it against observations. The theory tells you that there are these 3 curves, and those 3 should go through a particular point. And this is exactly what happens. So with this new perspective of atoms of space-time, you can solve this cosmological constant problem to a great extent. You can bring in a new perspective on it, and you can solve it, and that solves one of the greatest mysteries, we claim, which was around for several decades now in this area. So let me skip this. So yeah, this came from somewhere else. Okay. So let me now sum up what I have been talking to you about. The first point is that we do understand the evolution of the universe from a fraction of a second to about 14 billion years. Let me repeat that doing this is a great achievement in science, and cosmologists have done it. So we do understand how the universe is evolving, how it was behaving, how structures like galaxies and clusters of galaxies and all these has formed, and we have direct observational evidence for most of them. So this is no longer a theoretical speculation. We do understand how the universe behaved for most of its lifetime. The vacuum fluctuations, because the vacuum is no longer an empty region, which was generated in the very early universe, acts as seeds from which these gigantic galaxies which we see today have come out of. So there is a beautiful synergy between microscopic quantum fluctuations and very large scale macroscopic gravitational phenomena in this universe, and we see this synergy. There is something called cosmological constant, which is the fourth fundamental constant other than the Newton's constant, the G, the Planck constant which governs quantum theory, the H, and the speed of light c, which governs relativity. There is a fourth constant in the universe called the cosmological constant. This effectively contributes about 70% of the energy density today, and it is accelerating the universe. We know that it is accelerating the universe again from observation. So as I said, the greatest challenge was to understand the numerical value of this cosmological constant, that you need to look at things from a different perspective. If you do that, you will be able to explain the value of the cosmological constant. That in turn would require another paradigm shift in our understanding of gravity. Thank you very much.
Thank you very much, Paddy, for an amazing talk. I hope all of you enjoyed and had a great insight about the universe that you're living in. Time for questions. And I would be, okay, from here is better to see. I'll be trying to catch up with the raising hands.
Can we also make comments?
Yep, sure. Do we have another microphone, by the way?
We have the cube. You can catch it solved.
Jesus. Okay. All right.
Okay, I just want to make a little comment as a philosopher here. Thank you for your lovely lecture. And I just, you mentioned a few times this is observational, this is based on observation, this is not philosophy. So I just wanted to say that I noticed that there is a lot of similarities between cosmology and actual, like what we do in philosophy. For example, using deductive reasoning to deduce the value of gravitational constant, a theory of emergency, talking about paradigm shifts. Those concepts were also developed and used in philosophy. So I just wanted to add that, so that yeah, just wanted to say that. Thank you.
Okay. One technical comment. Please speak a bit louder because there is a problem in catching the audio. Please.
Okay.
Next.
Where should I throw it?
Oh.
Next person is there is someone.
Someone here?
You said sometimes you said that it's completely random, like the movement of electrons around atoms. Do you think it's really random, or it's just missing information?
Which one are you referring to? The movement of electrons in the atoms is not random.
All right.
I don't think I said that. Yeah. So can you clarify which of my comments you are referring to?
For instance, like
The vacuum fluctuations are random. Could it be that what you are referring to?
Yeah.
Okay. So the vacuum fluctuations are strictly random. It is described by what in mathematics is called the Gaussian random variable. So they are like the bell-shaped curves, and the fluctuations in the energy or in displacement in the vacuum fluctuations is completely random, and it is not that we are missing information. This is an intrinsic quantum mechanical phenomena. When you say that I cannot measure the position and the velocity of an electron simultaneously, it is not because I am missing information or my resolution of the instrument is not good enough. With infinite accuracy, even if you measure, you will not be able to measure both of them simultaneously because one measurement will disturb the other. So it is not missing information, it is genuinely random.
All right.
That is what quantum mechanics taught us. It is very surprising, but it is true. Yes, there is a hand going up there. Okay, there is. Oh, yeah.
If the universe is expanding forever,
Yes.
does this mean that there will be a point in time in which life will no longer be possible because the energy or the warmth of the universe will be spread out in a bigger space?
Mm-hmm.
I don't know if this makes sense, but
Yeah, this is really true. If the universe is expanding forever, which is what we believe it will do, if there is this, all the ideas like this accelerating universe, etc., are correct, which we believe is correct. So as it goes on, the large-scale universe is expanding, but the solar system is not expanding. Sometimes people ask if everything in the universe is expanding, solar system is expanding, Earth is expanding, meter scale is expanding, I am expanding, then how do you measure this? You may be expanding for completely different reasons. It has nothing to do with cosmology. Okay? So the expansion of the universe is at very large scales. So if you have a local planetary system, whether life is sustainable there, you will become more and more isolated and you will stop seeing stars and galaxies, etc., from the other galaxies, etc., as time goes on. But whether the life can be sustained in such a very cold universe is a completely different question. And most people believe it cannot be, but then we know so little about life. Okay, so cosmology is easy, life is difficult. Okay, so it is not an authoritative answer, but that is what most people believe in. You are quite right.
Good catch.
Yeah, but I believe there was a hand up there, but you can finish and then throw it back to him. Yeah.
I've been lucky enough to attend lectures from a lot of famous lecturers around the world, and I'll say this is the best lecture I've ever heard.
Thank you.
Thank you.
Okay, okay. I have one question concerning the expansion of the universe. From the information that you showed in the lecture, the universe is around 14 billion years old, and at the moment it takes around another 14 billion years to double in size. And I've read before that some scientists theorized that it might happen that at some point the universe starts collapsing. Is that a possibility? So that the expansion reverses?
Yeah. So this is what was encoded in that parameter called omega. The value of the omega determines whether the universe will expand to a maximum size and will collapse back, or whether it will expand forever. The current observations suggest that it will expand forever. So it is not going to collapse back. Okay? So that is a statement based on what we know about the universe observationally. It's not going to collapse back.
Okay, thank
Yeah.
you.
You mentioned that if the universe is static, then the night sky should be as bright as the sun. Why is this?
Okay, so that was the technical argument that if the universe is static and it is filled with stars all the way to infinity, every line of sight will hit a surface of the star like the sun. Now, if you take the disk of the sun and you ask how much light you are getting per unit area of that, if I move the sun twice as far away, then the size of the sun will shrink and the amount of light you get will also be dimmer. But they both go down in the same ratio, as a result of which the amount of light per unit area of the disk will remain the same. This is called the surface brightness. The brightness of the surface does not depend on the distance from which you are measuring. Therefore, the night sky, since every point is going to hit a star, should be as bright as the surface disk of the sun. Okay, so it sounds very paradoxical that with such simple argument which I can present in about 60 seconds, you can get a conclusion about the nature of the universe, but it is amazingly true. It's a very sound argument.
You said there's expansion of the universe, quite obviously you said, but it must be relative in some sense, right? Because if everything would expanding in exactly the same degree, then there would be no expansion.
Yeah.
It would just stay.
Yeah, but that is what I was mentioning. Everything is not expanding. Galaxies are not expanding, solar system is not expanding, Earth is not expanding, meter scales are not expanding. The word expansion, unfortunately, we cosmologists are to be blamed because we use the term expanding universe in a technical sense. But the common man understands expansion from the dictionary definition in a different sense. So when I say universe, first of all, there is no such thing as universe. Universe is just a collection of all that is in it, like galaxies. So let us assume for definiteness that the universe is a collection of galaxies. So when I say the universe is expanding, what I mean is not some abstract entity called universe is expanding, but the galaxies which form, the collection of which forms the universe, the distance between the galaxies is increasing. The size of the galaxies are not changing. It is only the distance between the galaxies which is increasing. That too, distance between very far away galaxies is increasing. If you think of it like that, there is nothing relative about it. It is an absolute phenomena. And it is also not expanding into anything, because that is another confusion many people have. When I think of a balloon which I blow air in, it expands. It is expanding into the three-dimensional space. But the universe contains everything. So what can the universe expand into? It cannot expand into anything. So you should think of expansion of the universe. Whenever I say expanding universe, you should interpret it as distance between two distant objects is changing in time. So in that sense, there is no contradiction.
But if it increases, then it must increase like in some direction, right? Like otherwise you could say like everything stays in the same.
No, the direction is readily outward. You sit here and you look at the galaxies and they are all moving away from you. You go and sit in another galaxy and you will find that all these galaxies are moving away from you. So it is again an absolute statement from every point.
Are the universes, the planets that are just getting smaller? And that's just...
At the scale of planets, at the scale of solar system, at the scale of galaxies, none of these things happen.
Okay.
Right? Okay. Uh-oh.
Okay, I have one more question. When we can look back in time by using telescopes, is it then not also possible to look in the future?
Unfortunately not, because the light comes from the past to us, and it is that light which I am seeing. Like when I look at you, I see you from the light emitted from your face a fraction of a second earlier. But I cannot figure out how you would look a fraction of a second later, because there is no light traveling backward in time. So that doesn't help.
Okay.
It would be lovely, but it can't be done.
You said we need to look at gravity as an emergent phenomenon if we are to understand cosmology better.
Right.
So how did this idea of looking at gravity as an emergent phenomenon emerge in the first place?
Okay. So very long back, purely from theoretical ideas, a person called Sakharov, who was a dissident Russian, and he was a physicist, well-known physicist, suggested that the gravity should not be a fundamental interaction, but it should come like elasticity. Right? If you think of fluid mechanics or elasticity, like the bending of rods and vibration of rods or vibration of bridges, etc., that is what elasticity deals with. Fluid mechanics deals with flow of fluids, but flow of fluids can be studied on its own, but the fluid is made of molecules or atoms. But in order to understand how water is going to flow, you don't really need to know what water molecule is made of and how its dynamics works. So the people from that point of view started thinking that gravity is probably should be thought of in this way. It is also motivated by the fact that all the conventional methods of putting together the principles of quantum mechanics and gravity failed. Every once in a while somebody comes up with some idea and it goes on for 20 years, 30 years, 10 years, depending on how strong people are pushing it. There is a lot of hype and a lot of hope, but eventually all these ideas have fallen on the wayside. And many of us, like our motivation was that we thought that that is probably because we have misunderstood gravity. We have probably understood quantum theory correctly, but we have misunderstood gravity. And if you take fluid mechanics and you try to apply laws of quantum mechanics to flow of water, you will get somewhat nonsensical results. So the theoretical nonsensical results which people were getting, we thought is because of this, and therefore gravity could be an emergent phenomenon.
I've got another question. You told us all the galaxies are moving away from each other.
Mm-hmm.
But at one point you told us Andromeda is
Yes,
coming.
that's right. I was waiting for somebody to ask this question. It is true that in the local group, the galaxies are responding more to the local gravitational pull rather than to the expansion of the universe. In fact, this is very closely related to something else which I was answering. If you go to the planetary system, the planets are all just responding to sun's gravity. Even though the entire cosmic gravitational field is available, this dominates over everything else. That is why at small scales things are not expanding, and Andromeda and Milky Way are not going away from each other. They are actually falling towards each other. But very large scale, if you take our local group of galaxies and some galaxy in the Coma cluster, they are going further away from each other. So it's a very large scale phenomena. I actually mentioned that hoping that somebody will catch me on it. Very good.
Okay.
Yeah.
Okay, this is the last question, and Paddy will be around here, and you can catch him on later on. So.
Not really, but that's all right.
Okay.
Yeah.
Okay, thank you. Then I have a compliment and a question. And the compliment is that I do find people interesting who dive with colleagues into very difficult things and trying to explain things for themselves to understand. Those people are very interesting to me. But other people who do the same but also explain difficult things to a generic public, a generic group of people, they are even more interesting. So thank you for trying these
Thank you.
over and over. And now this group tonight. My question is, if we are really looking at the cosmological constant, and so many things depend on that, is it, to your opinion, really a constant, or will that constant in those large scales be not really a constant? Can it be changing? And do we think that it's a constant?
Mm-hmm. Yeah. So there are people who have tried models in which the cosmological constant is actually changing with space and time. So it is not that people have not looked at it. Then you can put it into your mathematical equations and you can ask what kind of universe it will lead to, and then you can test it against observations. It turns out that all the observations which we have till today is consistent with the cosmological constant being constant in space and time. In fact, some 10 years back, I took a bet with a colleague of mine that all the observations will confirm it, and he paid up last year. Okay, so there is money to be made in cosmological constant. So this is again an observational constant. I mean, of course, I have my theoretical bias because my model suggests that it should be a constant, but it is very important that you keep an unbiased opinion and you test it against observation, which people did. There is a whole lot of models in which it changes with space and time, but all those models, when you test it, they can only put a bound. If it is changing less than what we can detect. Okay, so I would believe, and I would again venture to take a bet that it is a constant, and our observations will confirm that. Okay.
Thank you very much. Thank you for your time. Sorry for the advertisement in the background. we have a little gift for you.
Thank you.
Veronica.
Thank you very much. Yeah.